All right, so looks like my audio is popping up and down, so that looks good. So I guess we can go ahead and get started. It's 4:25 Thursday, March 26, 2026. Somewhat hard to believe in my mind that we are now after spring break, so I hope you guys had a good break. Welcome back to reality in some sense, right? To finish out the semester there. One of the hard things to believe is we're sitting in Southeast Kansas at this point. It's March and it's what, close to 90 degrees today. Yeah. So that is crazy. Driving over here from Southwest Missouri, I can see all the dust basically blowing across all those plowed fields there. It's dry out there. Welcome to our neck of the woods, I guess.
Yeah, I think it's supposed to get down to almost freezing Sunday night, was it?
Well, that wouldn't be surprising to me. What was it? A couple weeks ago, I think it was snowing on Monday and it was 80 on Friday, type thing. So
Right, right.
that time of year. All right, so welcome back again. Trying to get my mind right here. We've had a week off. Hopefully, you enjoyed it. Last time we talked about Chapter 7, mixed integer linear programming is the way I think about that, or MIP problems there. The whole power behind, hey, now I got linear programming models and not only real decision variables, but I've got binary and I've got integer decision variables, right? And that unlocks a whole nother realm of modeling capabilities that we just kind of really scratched the surface of there. So hopefully you guys appreciated at least some of the power that you were tapping into there, and also got to appreciate that without experiencing computational complexities in some sense there, because yes, there are different algorithms running there when you're running the integer and binary based programs than when you're doing just strict real decision variables there. But from where we sit, as far as nice, we focus on building that mathematical model to fit the business problem, and then we let the solvers basically do their thing essentially. And that's why we pay the Grobies, the IBM. I think has a solver there out there as well there. And so I like where we're sitting there. So tonight we are going to somewhat hit the peak in my mind. Not necessarily so much in complexity, a little bit in complexity, but we don't get too much into the mathematics of it terribly bad. But up to this point, we've talked about linear programming, chasing optimality in terms of minimization and maximization of an objective function. We will continue the idea of chasing optimality tonight, except for now we tweak it a little bit. Tweak it a little bit. Why? Well, things get a little messy in my mind. Basically, they have now the ability to have nonlinear characteristics inside of a constraint or inside of the objective function there. Well, what happens there? Well, that complicates things, right? A little bit from the modeling, you could say it complicates things, but also complicates things greatly from the solver side of things. And we'll talk a little bit about some of the things just at a casual level in some ways from what the solver could possibly be doing. Our last lecture problem tonight, we may experience some of those pitfalls a little bit as well. And so that's the agenda for the evening. I've already got our Docker container up and running for the class as we have throughout the semester. So we're in lecture. We're now jumping out of linear programming and now entering into nonlinear. Just a single lecture here. So we'd hop into here and I'll blow up in a couple notebooks here. Let's go ahead and let the first one run and we'll get going. All right, so it's a little more readable for you guys here in class. Nonlinear optimization models, like I talked about, basically you're still going to be thinking in the same ways as far as, hey, I've got decision variables, I've got constraints, I've got an objective function. That all's going to stay the same. You can think of that same mental cycle that you've been running throughout the semester. That's all good. The only problem is now that we're going to see potentially some nonlinear terms in there. A polynomial may jump out in the objective function, for instance. That's a problem for the GLPK, the junior linear programming kit solver there. It's going to have problems doing that. So we need to bump up the solver to a different solver today. Just give you a few examples of places in business. I like to tie everything back to real business problems. We're not pure mathematicians in this class. No, no, no. We are more on the applied mathematics side of things, right? That's why we sit over here in the kind of the engineering realm of things and not over there in Yates Hall on main campus for those of you that are around PSU itself there. And so Examples: marginal production cost, marginal in the sense that they are tied to the volume I'm producing, and a volume discount, right? That does make practical sense, right? Especially if you consider things like setup times and you're amortizing through their learning curve type situations there. That comes to mind as well. A lot of problems that we've talked about at this point are, hey, we assume infinite demand essentially there, right? Whatever you make, I can sell essentially has been a theme that we've had there. Is that really reality? Probably not exactly. Do customers, are they sensitive to the price of a product? Definitely, right? As far as, hey, I may be willing to buy a can of pop for $1. If a can of pop's $5, no, I ain't going to buy that, right? I'll go thirsty at that point. So there is a relationship there as far as the demand and the price of a product there. So when you think about the revenue that's going to be generated, when you're talking about how many units sold versus the price of the unit rented, right? Now you could have a nonlinearity when you take those two terms and combine them. Total cost of loans. I don't know if anybody's in here doing that, but I definitely do look at those things when I go to buy a vehicle, a car. When I look at our mortgage that I got on my house, I am computing in my mind, not just in my mind, but actually on Jupyter notebooks like this. What is the total cost of that loan over the life of the loan, 30 years, 5-year loans, depending on what we're talking about there. That is definitely not a straight line. If you look at the graph of the amount you owe the principal on that loan over time, right? That is not linear. No, that is non-linear. It shapes about like this essentially. Then you start asking your questions as far as, hey, if I put a little bit more down every month, how much does that change, right? How much does it shorten the loan? How much does that save me overall, essentially? Again, non-linear world at that point that we're talking about there, but very practical sense there, especially as we're all, I mean, I'm the oldest one in the room here probably, but we're all relatively young, right? I mean, I know I'm balding a little bit here. You can see the grays here as well. I blame my wife and kids for that, but we all get there. All right, so to get just talking with things that are a little more tangible for us, let's visit the same problem we started way back in chapter 2, right? It's a good problem, I suppose, for a teaching example. We talked about selling golf bags, standard deluxe golf bags. At the time, we basically said, hey, they got to go through these operations. That doesn't change: cutting, sewing, finishing, dyeing. There's certain factory burden associated with making a bag go through the sewing department. Half hour for a standard bag, 5-6 an hour for the deluxe bag. The sewing department has 600 total hours there. Can't run out of capacity, essentially, right? We've seen this before. And so we also, in the very first problem, said, okay, we need to talk about maximizing profit. In this case, we just gave you profit contributions there: $10 for one, $9 for another. I'm hoping at this point, as we are been talking now for what, 9 to 8 weeks, something like that, at this point, that's an easy problem for you there. Thinking about the relevancy of this class, I did get a little devious, so to speak, ornery, so to speak. We actually had a interview candidate at the place I worked. He interviewed his second interview, I think, roughly 3 weeks ago. I gave him our assignment problem from chapter 6. It was funny to watch his face get a little nervous there when he was starting to look at that problem in a stressful interview software development situation there. He would have fallen into the trap of brute force using the calculator, looping type things. And we talked a little bit tangentially about, hey, when that problem gets big, you're going to have problems there, essentially. And so we
Did
were
you
able,
give him partial credit?
he did get an offer. I'll put it that way. So yes, he
Nice.
passed. I think he's going to come to work with us potentially here in the next couple of weeks. Funny enough, I actually used that same problem a little bit in a conversation I had with my colleagues over there just this week. Yesterday, was it? Yeah, I think it was actually yesterday I was talking about that. I talked for roughly an hour and 45 minutes, yammering on, kind of like you guys here talk to me. It was a little more conversational, but basically used Claude Code as far as an LLM. If you can use Claude Code and say the right words, like, hey, this is an LP assignment problem. I want you to use Pymo. It'll actually create the model for you and solve it. Oh, wait, maybe I shouldn't say that in a class like this where you guys are going to be potentially using that, right? I still am very much in favor of you guys need to use the tools around you, essentially. I do not shy away from that. So if you guys want to play in that world, go for it. But I suppose
understand what you're doing, right?
exactly, be able to audit what comes out of that thing, right? That's the big thing.
Yeah.
Yes, yes. All right, so you guys would have developed something like this. That's what we basically did in chapter 2-ish, essentially talking about these things. But let's make this a little more complex, if you will. And the little more complex parts is saying things like, well, what if we have a relationship between price and demand? And that's what these two formulas here relationships, expressions, what do you want to call these things? Their equalities, essentially, are at the bottom. We have X sub S and X sub D. These are the amount of bags that we're going to produce and sell. But correspondingly, now we have a P sub S and P sub D. That is the selling price of the standard and deluxe bags, respectively, there. Now we've got this relationship. Okay, so with this relationship, again, the problem changes a little bit. We're still wanting to maximize profit. We'll say that there's cost tied to these. I think that's a little bit farther down. Yes, here we can use this information to get revenue. Here we also need to consider cost. Cost will be a little nicer. We'll just say they're static values. $70 the cost to manufacture a standard bag, $150 for a deluxe bag. Yes, you still have to obey. At some point, we'll look at the constraints, but at this point, let's throw the constraints out. Let's say the factory has infinite capacity. That's the unconstrained part of this heading, essentially. So again, just knowing what these variables represent, knowing the cost here, the idea is, can we come up with an unconstrained problem, essentially there? Maximize the profit. I've given you relationships for price, demand, and cost at this point. Hey, let's see if we can solve, assuming that there are no factory constraints, what would be the best values for the prices as well as the demands? You could calculate one and then back calculate the other there. All right. So with that being said, let's see if we can use good old Excalibur to do some bits here. Maybe I can actually just copy and paste would be the easiest thing here. Hey, now it's right there. Look at that. All right, just give me a second to get kind of calibrated with the ink pen here.
What is the goal of this chapter?
Nonlinear optimization is the goal. So basically, we're going to do the same stuff we've been doing, except for now we're going to have some sort of nonlinearity in every problem. Mm-hmm. So instead of everything being strict inequalities, strict equalities in there, right? Now we're going to have something like an x squared term will throw up in there. Potentially a trigonometric function could even throw up in there. That breaks things that we have been talking about so far. Yeah.
I started already to stop understanding.
Don't stop. Just appreciate it at this point.
I know, but it's because 1 week to learn the whole chapter for me it's too
a heavy burden.
What?
Heavy burden. Yes, that
heavy
is a lot. Yes. Well, hopefully your mind at this point, I'm assuming that it's like saturation. Think of it as a sponge, right? You come away from Thursday night, it's soaking wet, right? Now you've had a full week for that thing to dry out, right? You're dried out, ready to sop it back up again. That's one way to think of that.
Yeah. But I was talking about the previous chapter, so I stopped to learn properly.
Oh, the binary and yes. All right, so we need to come up with an expression for revenue here, right?
Right.
Revenue is what? Well, it's the sell price times how many I sell, right? Very simple terms here. Here we're talking about two different things. We're talking about standard and deluxe bags.
Yep.
So we calculate the revenue generated from standard bags. We add it to the revenue calculated from deluxe bags, right?
Yep.
Easy peasy. So we say something like, well, this is P sub S times X sub S plus P sub D times X sub D, right? Looks good. We want to get this really down to a expression for profit with two decision variables here. And so we do have a relationship, right? We could eliminate like a P or eliminate the X's using that expression that's tucked up right here in the corner, right? There's expressions there. In my mind, to follow the lecture notes too, even though I think you could do this either way, let's isolate the P sub S's and eliminate those. So we'll aim for expressions here, first revenue and cost, and then we'll use those two to get to profit. But we just want to have the X's in there, eliminate the P's, if you will. And so I can do that off to the side. Maybe we just draw a line here. Looking at this first one, if X sub S is equal to 2250 minus 15 P sub S, get it close to the side there, causes a little issue. Then what do I write this? I could say P sub S is equal to what? 2250 minus X sub S all over 15. Right? Sounds good. Just a little bit of simple algebraic manipulation. Let's do the same thing for the other one. It's x sub d is equal to 1500 minus 5p sub d. We could say p sub d then is equal to what? It looks like 1500 minus x sub d all over 5. Now, what do we do with these p sub d, s and p sub d expressions? Well, I can back substitute over here, right, to replace these over here for that. So I could say that's equal to something here, 2250 minus x sub s all over 15 times the x sub s plus p sub d, which is 1500 minus x sub d all over 5 times the x sub d there. At this point, this is where you would start being a little nervous as far as from the linear to nonlinear transition, right? I'm thinking those x sub s and x sub d will be the decision variables, and here I'm starting to see the quadratic format here, right? That x sub s here is going to get multiplied by this x sub s here. Oh, I've got an x sub s squared, right? That's breaking everything that we've talked about up to this point in this semester there. But we're okay. We'll keep rolling. So I need to reduce this a little bit as far as, okay, it's what, negative 1/15 x sub s squared plus, I have no idea off the top of my head what 2250 divided by 15 is. So I would use calculators. That's 150. Then I'm seeing minus, now I've got 1/5 x sub d squared. I can do that one though, it's plus 300 there. So now I've got an expression for revenue there. It is a quadratic, right? I've got the squared terms in there. Now we need to take a little bit of a break here. We'll work on cost. Well, cost is pretty easy, right? I've just got unit cost here for a standard and deluxe bag there. It's a static value there, so that's easy to do. 70 times x sub s plus 150 x sub d. Easy enough there. After an expression for profit though, right? Well, profit is revenue minus cost. Easy enough. I now can just do a little bit of algebra essentially. So I'm first going to look at the squared term here. It's negative 1/15 x sub s squared. Nothing down here, so that just comes straight in. The x sub s, I've got 150 minus 70, so that would be what, plus 80 x sub s. Negative 1/5 x sub d squared there, and then what? Oop, I missed something right about here, didn't I? That's 300 x sub d there. 300 x sub d minus the 150 x sub d, that's positive 150 x sub d. All right, so this looks to me like an objective function. I've got, if I wanted to maximize profit, I would then maximize that expression. It is a function of two decision variables, right? X sub s, x sub d, and we'd go about our business there. All right, so question becomes, how do you go about that, right? Very good, got to that, that's great. Well, one way you could do it is really just graph it, see what you're playing with. It's two decision variables, right? It'd very easily to consider that one x, one y, profit in the z direction, essentially three-dimensional graphs, right? We are three-dimensional creatures, so it matches nicely. In this case, you pick somewhat arbitrary values here. It looks like in the two different axes there, I went from 0 to 1,000 there. The z would be the profit side of things, and you have this nice little shape here, right? Kind of a hill, so to speak, right? You could do this somewhat by inspection and say, well, I mean, the top of the hill is roughly somewhere in here-ish, right? You'd find a good solution. May not be optimal by that point, but you'd be pretty close. Or we could do some solving at this point. Let's talk about solvers. Looks like here I'm doing the Pyomo version first. So let me go ahead and just come over here and get a new notebook here. For the Python side of things, we should be pretty much doing this the same way as we always have, as far as that's boilerplate code at this point too. Import Pyomo as PE. We would still have to create a model. We know all the data at this point, so that's why we go concrete model. Golf bags.
Is it that we're gonna face some integers in derivations here?
Somewhat.
Integers and derivations?
No, actually.
No?
No. I try not to.
Swear?
I don't think so. I did review the lecture last night, but it was getting somewhat closer to 11 o'clock or midnight. So could I have missed something? I'm not sure. I know where is there? There is a little bit of calculus that peeps up either next week or the week after. I can't remember. Probabilities comes into the simulation lecture. I know. So we don't get too deep there. I don't require too much there. Again, I have a very mixed audience that comes into this class. If I didn't, we would go to the depths at times. All right, so we created this. We need some decision variables here. We'd say x of s, sure, is a PE dot var domain is equal to, well, let's assume they're not negative real still. All right, very good. Still very good. And then what are we doing? Well, I've got the two variables defined. I just need an objective. Then I would just be able to write my objective out here, I suppose. All this, yes, I wrote x sub s there, but everything else to this point is kind of the same as we have been doing. This looks awkward. No, does it awkward? Oh, wait. There we go. Just to make sure we're understanding here, I forgot a little bit of Python syntax there for a moment. The caret replaced by the double asterisk for the ampersand here. Just kind of checking my logic to make sure that we're all good here. I think we're so far so good. And typically at this point, we would go on to the constraints, right? But we said this was an unconstrained problem there, so we should be good at this point. Then you would typically have said before, solver is equal to PE solver factory GLPK solver.solve m t equals true is a lot of things what I would say, right? Print the output to the terminal. Uh-oh, we have an issue here. What is the issue? Oh, here we go. This is exactly what I wanted to show, so very good. Everything's going somewhat according to plan at this point. What does that say? Model objective, okay, so something's wrong in our objective function, contains what? Nonlinear terms that cannot be written to LP format. Here's the first thing that we had to change, right? Now we have nonlinear terms. We can't use that linear solver for it, essentially, there. So that's what this thing's complaining about. GLPK, it wants linear things. It will allow you to do integer and binary decision variables, but it is strictly a linear solver there. So got to do something different here, essentially. Well, what's somebody to do? Well, I guess you could ask ChatGPT anymore, and it would tell you some solvers there. I've already baked into our Docker container another one called IP-opt, I believe. And you could say IP-opt. So we're just at this point just changing that string is all I'm doing because I've done a little bit on the Docker side of things, and we're just flipping the solver. Don't use this solver, use this other solver here, IPOPT. Hey, looky there, and it didn't have a nice red thing here. We're using IPOPT. Notice here it's what? A library for large-scale nonlinear optimization. Sounds great. Open source here. I didn't pay anything for it. Don't have to worry about the licensing side of things, so that's great. And what happens? It goes and prints off some stuff here, does some stuff. Hey, even better here. We found an optimal solution. But that is concerning there. What did I mess up in the objective function? I guess is my next statement. We will compare notes. Oh, I didn't put a sense on here. Shame on me. The default probably is minimization there. A lot of these problems are like that. Rusty after being gone a week, I suppose. Very good. Basically, we chased the other way, right? The sense we didn't include, I assume it went to minimization. It basically brought it all the way down to 0 very quickly. And then we say, okay, maximize it. Then what do? We end up with a 552.125 there. You should probably be able to say m.display still here and get a summary of it as well. 52.125, roughly 600 and 375 there. A little bit of floating noise there at the end there. 600 standard bags, 375 deluxe bags there. Essentially, that's the very quick computer solution there. Notice one of the nice things I'm trying to do for you here is I've already configured inside that Docker container IPOPT. As far as I've got it installed there, I set up the system path there essentially. So that way, all you have to do from the Pyoma situation is instead of writing glpk, you write IPOPT there essentially there at that point. There are notes I think that you can find there in the class documentation as far as how to install it on your local system if you want to do it that way as well. I should also show you Excel. Excel's going to be a slight twist as well, so let's just do that right here. We need decision variables. I'll say standard bags and deluxe bags here. I have an objective function. I do want to maximize something here. And then we would be writing the same thing out here is equal to negative 115 times x sub s squared. Now I can use the caret plus 80 times x sub s minus I think it's 1/5 times x sub d squared plus 150 times x sub d.
Shortcut to the power sign, like
power sign. Oh, the caret?
Yeah.
This right here?
Yeah.
All I do is I hit let's see here. Shift 6. Usually the number 6 is the caret.
Shift.
Yeah.
Okay. 6.
All right. So at this point, we've told the Excel worksheet everything it needs as far as the model goes. We're not having any constraints at this point, so we can pass it to our solver. So right up to the solver as usual here. Let's see. I need to set the objective to the yellow cell C8. I want to say maximize. I want the solver to be able to play with these two cells. And this is actually ready for me at this point, right? Make the unconstrained variables non-negative. That's fine. Yes, I do want them to be non-negative, so that's good. Right now, it's set the GRG nonlinear, right? Up to this point in the semester, you've flipped that to the simplex solver there. Today, no, we leave it there, essentially. GRG nonlinear. Yes, you can get into the options here. You could also play with the evolutionary side of things as well this week. To play around it here, we will actually probably play around with that at the end of the hour there. For this problem, it should be very straightforward and solve. And there we go. And so we've got the same thing going on here as far as it looks like 52,125 and 603.75 for the optimal solution there. Pull that up so it's a little easier for you to believe me there. Easy peasy at this point, right?
Is there a reason why the Pyomo value came from 600 on the other side and 375 on the other side, and Excel came from lesser than?
Let me make sure I'm understanding what we're talking about. So the standard bags from Pyomo is 600. And the standard bags here is approximately 600. Deluxe at 375, Deluxe 375. Oh, are you saying like the 600 here is just slightly above 600 and the
Right, yeah.
I wouldn't read anything into that. No, that's just going
Okay.
to be numerical noise at this point. I would
Okay.
probably be a little bit more like this, essentially, that both of them I would round to the integer of 600 and 375 in my mind.
Okay. I just didn't know if there was a story there, some history. I don't know. So anyway, thank you.
No, yeah, I don't think there's much really to read into those things. Just a little bit different numerical things that are happening at that point.
Can you put any constraint to make it show you integer values?
Yes, you should be able to still mix and match those type of things as far as that goes. Again, you're adding on top of the complexity of the. Now you're mixing two different things, right? You're introducing, hey, this is nonlinear, and you're saying it's got to be integer as opposed to real decision variables there. These are two areas of complexity that you're forcing onto the solver. I can tell you that much. We won't have to deal with that, but yes.
I mean, to show integer values like 600 instead of the noise, no?
Yeah.
So it is possible to.
Yeah. There's a whole, again, I think there's a whole realm of subject. I'd go look at the Groby type stuff that they talk about as far as, yes, if you're going to do nonlinear programs and you're requiring integers, there's a whole little bit there of stuff you have to deal with.
It's a whole subject to make it.
Oh, yes. No, you are knocking on the door. If you really wanted to pursue this, these are things that you would be looking at very deeply in like PhD type of studies, essentially there.
Oh my God.
I mean, these are the depths you can go into in these very narrow focused areas. We're not going to get don the scuba gear or anything like that. We are on the surface.
All right.
All right, but just to show you, okay, yes, we had objective functions. We have solvers to solve these things, right? Slight differences. GLPK to IPOT. Okay, use GRG nonlinear in the Excel world. Don't use the LP, simplex LP solver. One of the things we've also done is see things graphically, and I wanted to show you that a little bit. Before we get into the actual constraint problem, looking at graphically there, let's look at the graphical approach a little bit from the unconstrained problem. And so that's where I've got this here. You said integrals, I'm not going to show you an integral, I'm going to show you a gradient. That's closer to derivative in my mind, so I did not lie to you yet. All right, so this was the objective function that we were playing with, right? Maximum negative 1/15 x of s squared plus 80 x of s minus 1/5 x of d squared plus 150 x of d. How could you go about solving that, right? I showed you the picture, that kind of shape, that hill, right? If you were saying, hey, you don't get to use Excel, but you have to come up with your own algorithm to solve it, how would you do that? That's an open question, right? And so one way you could do that is look at that as a gradient ascent problem there. Similarly, if it was a minimization, you'd say it's a gradient descent problem. If you've never heard of that, basically just think of it as a hill climbing exercise. You basically start someplace randomly on the hill, and then you tell yourself, okay, in this case, I'm going gradient ascent. I look around myself and say, what direction is steepest? Upward. You calculate that and say, okay, I found the steepest place upward. I'm going to step in that direction. I take one step, and then I, again, play that same thing over again. Okay, now that I'm there, what's the steepest direction? Okay, I find the steepest direction. I take another step. I step in that direction. You keep on doing this over and over again. Eventually, you climb the hill. That's basically the intuition behind gradient ascent. Now to talk about the mathematics of it slightly. I don't require this of you. This is more of a embellishment on the lecture, if you will, coming from the fact that I spent too much time in the 8th hall, most likely. This is one way to look at that decision variable, right? Or the decision variable, the objective function. Here I'm just saying, okay, yes, it's an expression of two variables, f of x of s and x of d, right? Think of it as a two-valued function there. This gets into the calculus 3, I think, if you go through the PSU curriculum there, where they talk about multivariable calculus. Instead of a derivative, you sometimes talk about partial derivatives to get the direction in there. And so that's all I'm doing is saying partial derivative with respect to x, partial derivative with respect to d there. Of this expression, that's what you end up with, those two partials there. Not again worrying about too much of the details. You can just agree with that's what it's doing. Then you define the gradient. This is the idea of the gradient here. You have the partial derivative in the given direction, here in the direction of the standard bags, times the unit vector in that direction. That's what this little bit here is. The little hat, basically, think of that as a unit vector. Unit vectors, from those that haven't heard that term before, it's kind of back to the physics side of things. Vector has two things typically, right? Direction and magnitude. Unit vector, unit comes to the fact that it only has a unit magnitude of 1, essentially. So all it's doing is capturing direction. No scaling there, just direction there. Here we got another one. It's two decision variables, a function of two variables there. So now we just say, here's the partial with respect to x sub d times the unit vector in x sub d there. We calculated those partials, so now I can stick that in here, essentially. Now I have the idea of the gradient. We're going to use the gradient to figure out that question every time I make a step. Which way should I go, essentially, right? So now we get down to our stepping formula here. Let's say I'm at some point, x sub s, x sub d. Talk about it as a little bit of a vector, or call it a row matrix, if you will. And then here's the formula of how we're going to walk. I'm at some place right now. I'm going to predetermine some step size h. I'll leave it at that. Predetermine some step size h. There's a little bit of a talk there that we could have. And then this is the gradient of the function at that point. So basically you say, okay, I'm at a point. I calculate the gradient at that point. That tells me the direction that's the farthest fastest ascent. Then I take a step in that direction. Now I'm at a new point. Now I repeat that cycle over and over again, essentially. That's what this little bit of Python code is going to be doing here. At some point, you have to have some sort of out mechanism there. As far as you loop that in an infinite loop, how do you know when to stop? Typically, you could say things like, well, only walk up to some set number of steps. That would be one way to out. Or you say, wait until the improvement in your score, in this case, I'm getting higher and higher, right? If I ever stop including getting very high, maybe from every 10 steps, I'm only looking to see how much percentage change I'm having. That'll eventually creep smaller and smaller. If I get past some threshold, halt at that point, right? There's another way to stop it. We pick a random point to start off. There's 100. I got a tolerance. That's kind of like the out that I'm using here. And I'm going to have, and there's 1,000 steps also, kill this thing. So I've got two ways to terminate the loop. And it goes through the walking step here. I'm computing the gradient. I'm computing the next step. I'm computing current profit, next profit, keeping track of things at this point, and then breaking out. In this case, it looks like I'd make 173 steps. Here on my start. Here's the next start, next profit. And what do? I go through this actual walk right here.
You're going to teach us how to make this 3D model?
If you want to look at the code, you can, yeah. Really not that bad. You just have to learn a little bit of the Python syntax. There we go. That's a lot bigger. So what did this thing do? Well, it started at 100, 100. That's this red dot right here. And what you're seeing here is the red dots is the path that walk took, essentially. Notice it's not linear. It kind of curves a little bit there. But at every point, it was finding the steepest route at every point in time. Also notice the step sizes are a little bit bigger, right? Here it looks like it's going big, but then as it gets closer and closer, I'm taking itty bitty steps here, right? I do believe I have a constant step size here, right? Yes, even though I have a constant step size, I'm like growing farther, right? Because as far as what you're seeing, that vertical depth essentially is changing there. And so basically what you do is you start walking, walking, walking. Eventually, I'm terminating here. What am I terminating? We said what was 300? What was the score? 600, 375. How close do we get to that here? 598.5, 375, right? Very close there at that point. I don't know if I'm on the very end or not there, but I'm marching right up to that point of 600, 375 is the idea there. So that is one way to think about it. I did hesitate here just to talk about embellishments on this. This is a fairly simplistic model. Yes, some people get scared. I have at least one person that I sit very close to at work that he sees things like this and he calls it satanic mathematics, essentially. I say that is real mathematics there. And the reason I hesitate here is an embellishment. This h here, that h here is constant, right? You can have even an interesting thing where that h becomes smaller and smaller as you walk farther and farther here, essentially. that I think is typically called simulated annealing. That comes from the foundry area down here as far as when you have something hot and it cools over time, right? Think of the atoms when they're hot, bouncing very, very quickly, very, very fast. And then as they cool, they slow down, essentially. There's kind of the idea. So there you go. That is one way you could do it without using GRG nonlinear, essentially. You could code that up in some way and solve it that way. At this point, we've only talked about unconstrained problems, and we're talking about easy problems in the sense that that was a nice, simple shape, essentially. Keep that in mind as we move through the lecture as well. Well, that problem was not totally unconstrained. There was constraints on it as well, though, right? The full problem would have looked something like that. The objective function is nonlinear. It's got that quadratic thing in there, but we cannot ignore the factory essentially as well, the limitations that there are. So all we do is we just add those back in. Those things remain the same from what we did 6 weeks ago or something like that when chapter 2 happened there. So that's all the same. Chapter 2, I talked to you guys about a graphical way to do it. I can still talk about you in a graphical way to do it, and maybe a good way to show that at this point. Assuming that first line there, the objective function was linear, you would know exactly what to do on a graphical one at this point. Hopefully. I mean, I can wish at this point that you retain that. I understand that's been a while for you. But what would you have done? You would have created the feasible region, right? You would have drawn that hexagon, you would have defined that, and then you would have went to the objective function, picked different values. Let's go through that same line of thought here. First, we do some work and define a feasible region. Hey, there we go. That unconstrained solution lies outside of the feasible region. That's the red dot there. 600, 375 are the points right there. Well, if that was inside the feasible region, it would be great, right? We'd be done. We'd be great. In this case, it's outside. Okay, we got to do more work, essentially. That's kind of the first check. We can still do the same idea of picking different values for an objective function and now plotting them. Our problem is now that was a quadratic, had the squared terms in it, right? And it was not a linear objective function. I'm not going to get straight lines here, right? I'm going to get some other shape. In this case, I get ellipses. That's what each one of those ellipses there is. So basically what you do is you start with feasible region, you try the unconstrained solution, doesn't work. I pick some value for the profit, 52,000, forms the green circle. Does the green ellipse, does the green ellipse in any way touch the feasible region? Simple question, right? No. So you decrease it in this case, right? We're on an objective function. We're trying to maximize it. So we start throttling it down. As I decrease it now to 51,500, the ellipse grows. Think of this a little bit as a topological map, I think is what they're called. Everybody's seen those maps before, right? Where you're looking from the air, looking down, and they have different lines on there that talk about the gradients of the ground, right? The lines are very, very close together. It's steeper essentially there. That's basically what we're looking at here. Think of it looking down on top of this hill, and we're going down the hill, so the hill's getting bigger and bigger and bigger, if you will, as we drop down. All right, 51,000, okay, still not there. 50,500, still not there. Oh, 50,000, did it hit it? Getting close, right? 49.5, okay, now we're somewhere between 49.5 and 50, right? 50,000 there. We've bounded it at this point. Yes, at this point, you could drop down to whatever step size you want and really hone in on it. At some point, it's going to kiss this interval right about here, right? And that's what we would call the optimal solution there. That would be kind of your working toward the graphical solution. Okay, so notice that's different than what I talked about in chapter 2. Chapter 2, I was saying things like, well, it's all linear. What does that mean for nonlinear? You only have to check those vertices, right? That was the big thing in the simplex algorithm.
Yeah.
Does not apply at this point. Now we have a little bit harder of a problem.
What do you mean? Like now we don't need to check a straight line.
Correct. Yes, before, as we looked at that, the simplex algorithm said, okay, define the feasible region. Only have to check the vertices. Only have to check these corners, if you will, right?
Yeah.
You were guaranteed that the optimal solution was going to be at least at one of those corners, right?
Mm-hmm.
That guarantee is no longer present.
Okay.
So now you have to do a little bit more harder research, right? If this unconstrained solution happened to be in here, we would have stopped altogether. So it could have been inside the feasible region. Now it's outside the feasible region. Now what am I checking? Well, I'm checking to make sure at least one part of those ellipses hit the feasible region. But where is it going to hit? It's not hitting at a vertex, right? It's going to hit somewhere right in there. So it's hitting along the boundary there.
And that ellipse is formed by the objective function.
Yep. There's some Python code in here that it's doing its work here to form the ellipses, but yes, it's all going into the objective function. That's where these values here should start looking similar to that. So again, it's obscured a little bit from what I've got going on here, but you can just believe me, yes, those are inspired by the objective function.
Can we put that on Desmos?
On Desmos, I don't know. I don't think I asked you for any graphical ones today, but you could probably play around with that a little bit. So yes, big difference here. In bold here, yes, the optimal solution. What is this? How do I do this? No longer known. No longer known. It's not a guarantee that the optimal solution occurs at a vertex. We got to do more work, since that's part of the reason that makes nonlinear harder, essentially, that we don't have those mathematical guarantees there. So at this point, how would you go about solving it? Yes, you could step down really close and try to get very close to it from the graphical solution. In reality, you wouldn't necessarily do that. What would you do? Well, on the Python side of things, I basically just wrote that before. If you look at the rest of this, oh no, I wrote all of that before. If you look at these lines, that's the exact same thing I would have written in chapter 2. Nothing has changed at that point. They're all linear expressions, so you write those the exact same way. Pass it to the solver. Now the solver has to be IP-opt because it's got that nonlinear objective. T equals true. It solves it out, obeys the constraints, and then you can inspect the result. In this case, we're sitting at roughly 49, 9, 20, 56 is the prof that would be yielded, and 460, 308-ish. We're using real numbers there, so it's going to float a little bit as far as the decimal points there. In my mind, I would, at this point, leave it as decimals. I wouldn't go down the path that you were kind of describing there before of my first initiation would not be to inform it and make sure it's integer decision variables in this case. We're dealing with hundreds of these things. They have something like 70 and 150 for the contribution. No, that was on the cost side of things. My first step would be do this first with real decision variables. I wouldn't doubt anything with the size of problem there. What's that going to do? It's going to get you a solution faster. In this case, I would truncate both of those floating point numbers if I was doing it for real. That gets me down to integer values, assuming I don't make 3/4 of a bag essentially there. And then I know since all of my constraints are greater than or equal to the fact that I truncated and brought those decision variables slightly down, I'm not going to overrun any constraint there. I've got a very good solution at this point. If I wanted to, then after I have that in the bag, so in case I spend the rest of the day and don't get anywhere, essentially, I would then go to that if you wanted to play around with the, hey, it's nonlinear as well as I need integer constraints there. That's when I would start pursuing that as a secondary goal. It's essentially at that point. It's one of those things I'm kind of hedging myself, though, that when the big boss comes to me on the next day, I at least have him something to give to him, and I can be confident it's a pretty good something. It may not be totally optimal, but I've at least got something going.
I have a. Can you go up a little bit to the graph?
Yes.
So to solve that problem, I know probably it's overthinking the situation, but can we discover the inclination of that line over there?
Which line?
The middle one. The one that will
this one?
We can the one we can see that will touch on the ellipse.
Mm-hmm.
So if we find the equation that forms that line, we can make it equal to the equation that forms the ellipse and find the point of intersection. Tangency point.
Tangency points would be the big thing. You're going to get into some mathematics here, maybe flirting with a little bit of calculus at that point, right? Yeah. If there were two straight lines, you said you can find the intersection of the two straight lines by solving a 2x2 system of linear equations, right?
I think so.
I think so as well. Yes, it's been a while from linear algebra, but that sounds right to me as far as what I remember back in those classes. But now that I've got a line as well as an arc there, I've got to work about some. You're right about the tangent point. You would be looking for that tangent point there.
Yeah.
So you'd have to figure out, okay, what's the best way to describe that essentially? Just thinking through how I would even start with that. Again, it's been a while since I've been in thinking about that part of mathematics. From the line segment, I would know a slope. At that point, I would be asking myself, okay, if I can figure out that slope, now where does that slope apply on that arc?
Yeah.
Can I figure out, well, what X and Y point on the arc is that slope at? That's where I would start hunting essentially.
Yeah.
Yeah.
So it is possible to make it.
Oh yes, I definitely think that it's possible. Yes, to do it by hand at this point. It's a geometric type problem there, not in terms of strict geometry, but you'd flirt with some calculus stuff in there.
Because I was thinking, for example, if I get lost doing the calculation in the way you teach it, if I could like discover the equation that form that line and make it equal to the equation of the ellipse and figure out what is the point of the tangency point. So,
Yes, you could go around that path. I would try the path that I'm going to describe first. It'll be easier for you. Yes. And yeah, the only thing I other hedge when you're saying that, I agree with the spirit, what you said. At one point, you're saying the equation, setting the equation of the line equal to the equation of the ellipse. And I'm like, okay, what that term means in your mind, that's where we'd have to determine, okay, what is that exactly going? Like how you would write that out essentially is where I would start questioning.
it's because it seems to be easier, since you already know the objective function and to discover the equation of a straight line where we know the at least 2 points.
Yeah. Determining the equation of this line segment is easy.
Yeah.
Easy thing, yes. All right, so we did it with Pyoma. I'll just show the Excel one. The Excel one, nothing too much to be excited about, I don't think. Just we're on the constrained side of things. This is what I had basically pre-baked essentially. All right, so a bunch of data stuff here at the top. Got decision variables here. I think 49, 920, 55 looks to be roughly the same that I had before. Not there, but here, 49, 920, 55. Yes, that's good. And so what are we doing here? We have decision variables. We've got the objective function, which that should be the same thing that I wrote before, just referencing those decision variables. And then this bit down here is the exact same thing we would have done up to this point in the semester, just writing out the constraints one after the other. And at this point, fairly easy solver dialog there. Just setting the objective, setting it to maximize. We're just setting the decision variables like we always have. In this case, they're all 4 less than or equal to. Do it all at once, essentially, at this point. Leave it at GRG nonlinear, and it solves at this point very quickly. So nothing too much there to worry about there. All right. I kind of hinted on this topic a little bit earlier, and it's the sense that in the realm of nonlinear problems, not every problem is equal in terms of difficulty or complexity. Hopefully that's intuitively pleasing to you. And really that comes down to these problems here as far as local optima and local versus global. So typically when I'm solving a problem, I want the global optimum. Makes sense, right? I want the highest height or the lowest low. Highest height if I'm talking about profits, lowest low if I'm talking about cost, for instance there. We would talk about that as global. Local, think of local as your local neighborhood. Just, hey, what are the points right around where you're at, like, essentially there. And so if you can keep those two thoughts in your mind, these next few bullet points are pretty easy. Local optimum, we're talking again, immediate neighborhood there. It's got to be a feasible solution. And I'm wording it as feasible solution with no better objective function value. So in that case, I'm trying to keep that both from the optima or for the maximum and minimum in the same line there. And the big thing is found near the immediate neighborhood. So we talk about local maximum. It's a little hill that's higher than any other hills, any other points around it. Local minimum is a small valley essentially there. Again, looking in those immediate adjacent points, you'd always see upward trends there. Global optimum, now we look at the entire surface that I'm dealing with that has all the feasible solutions on it there. So then we say global maximum, you're at the highest height of all the feasible solutions. Global minimum, the lowest low of all the feasible solutions there. Key thing data right there, we're talking about the set of feasible solutions in all those definitions there. There are some names for these nicer problems, convex and concave. If you haven't heard of those, think of umbrellas or bowls is what I think of. By bowls, like the bowl you'd eat your cereal out of, essentially there, or soup. More cereal when it's 90 degrees than soup, I suppose. Concave and convex. Concave, bowl shaped down. That's basically what we were talking about just before there, right? Your big thing about concave is this statement right here. Your local maximum is going to always be your global maximum. There's going to be one and the same there, essentially. That's why I was thinking of that first problem that we talked about when we had the negative coefficient in front of x of s squared, a negative coefficient in front of x of d squared, right? I knew that was at that point looking like this. They can't see me on Zoom, essentially, but basically it was the bowl shaped down, right? That was the umbrella as if you were hiding from the rain, essentially. And so those are very easy for the solver, right? Think of your gradient ascent problem there. Pick any point on the surface, do a gradient ascent metric. You may have to walk farther in some cases than the other, but you're going to find the top of the hill, right? Just from the logic we just described there. That's why I'm very saying, hey, those are easy problems there. Other characteristics is, besides what I just described as far as the quadratic, the square terms have negative coefficients, there's no cross products. No cross products, we never had an x of s and an x of d multiplied together, essentially. That's the way to think about that. The reason I talk about this in terms of these statements, as opposed to always graphing it, is because these statements that I've got highlighted there, those hold even after I get past 2 dimensions. By 2 dimensions, I'm talking about 2 decision variables there. If there's 2 decision variables, I can always plot that graphically, right? And it's very easy to see. If there's 20 decision variables, not so easy to see, right? So you have to hinge on these mathematical properties to figure out, okay, is it convex, concave? Is it something weird, essentially? That's where it gets to. Convex, now you shape the bowl shaped up, it's the soup bowl, right? Very good for minimization problems because the global minimum and the local minimum are the same, right? Now instead of gradient ascent, you look for a down, so it's gradient descent, and you go find the bottom very, very easily there. Now we have positive coefficients on those squared terms, the quadratic parts there, and then no cross products too. Again, no x times y, essentially, if those are x and y are decision variables. Unsurprisingly, what those look like, here's your typical concave, something about like that. That one's nice and symmetric. And there's your convex there. So,
What next?
yes, very nice, very smooth, right? So one bottom, one top, essentially, right? We like that. What we don't like are messy things. That thing at the bottom is very messy. Why is it nonlinear? Thoughts?
No. Exponential things?
Exponential things, yes, that is a nonlinear function. Yes, agreed. I also see some squared things happening in there with the decision variables x and y, right?
How did I know this? The powered stuff are powered also.
Yeah. There's some steps there, right, that you're picking up on, yes. This was actually, I grabbed a function out of the Lindu. Lindu, I believe, is a solver there. They had some API manuals online. I stole this from them, essentially. If you plot this, what does it look like? They've engineered this, basically, to look something like this. We're rotating it very slowly there. What do we have here? This is not a nice bowl, right?
We have one maximum and one minimum there.
Okay, be very specific on the maximum minimum. We have one global maximum. We have one global minimum, but we also have local maximum and local minimums there that are not the global ones, right? This is the problem. As far as, for instance, here's global maximum. Here's a local maximum.
What do you mean by local?
Local means it's the highest amongst all the neighboring points. So if I'm sitting on that on top of this hill, if I look right around me, everything goes down. That defines a global or a local maximum. But then you have to ask the question: is this the highest hill of all the hills? In this case, no. So it's local and not global.
I got it.
Right? Yeah. Same thing if we go underneath. I'm seeing one global minimum here. There's a local minimum there. And it's hard to see, but there's also a local minimum right about there. Why is this problem hard? Well, let's go back again to the gradient ascent idea. Gradient ascent, what did it start with? Pick some point at random, right? That's how you got to start. You got to start some point on there, and then you basically walk up the hill. Well, what if I pick this point right here? What's it going to do?
You're on the wrong hill.
Exactly. It walks up the wrong hill. Great way to put that. It's going to walk up that hill. Then it's going to terminate and say, hey, I've reached the top. Well, great. I missed the whole idea that there's a big top over here, right? Same thing here. I can walk up that hill. Gradient descent would have the same thing. It would be walking down. Heaven forbid also, in this one, this is a nasty looking thing. What if I picked a point way out there? The gradient isn't very big there, right? The slope's not very big. So it's going to have trouble even going very far very quickly, essentially, right? Yeah. If you have a flat surface, I've got trouble if I'm trying to walk up and down, right? Again, this is a very engineered expression, I think, to achieve this result there. Other thoughts there is that, and I guess that becomes the question: how do you go about trying to combat that? Right? You know these problems exist. What are different ways you do that? Wait for some smart guy to figure out, publish a paper. He'll wrap it up into some software and then bill you, right, for it. Essentially, that's one way things happen. Well, yes, that probably has happened at some point in history. There, we're long past that for these type of problems, and unless there's some novelties in it.
To figure out this, I don't know how to make it mathematically.
No, we're just talking intuitively at this point, so that's fine.
Yeah, you can just look to the 3D model, and you're gonna figure out that your point is not on the correct place to find the peak of the hill, right?
Okay, so you okay, very good. I agree with what you're saying. You hinged on the fact that you have a 3D model you can look at.
Yes.
What if you have more than, let's say you have 5 decision variables? What are you going to look at?
If I have 5, how many we have on this one?
2.
2.
The X and Y are your decision variables, then the vertical is the objective.
Yeah.
If you have 5, where are you going to put those 5 dimensions?
We don't have 5
dimensions. Exactly, yes, that's where it breaks down. Yes. That is where it becomes problems. And so that is the crux of the problem. Yes, we are creatures. God created us with 3 dimensionals around us, right? We are very comfortable with that. Yes, you could get a little bit creative with colors, right? That's a way to interject a 3rd dimension into charts like this. Size of dots is another way to do it. Opacity, right? Or things that you could play with. All these are going to be very hard to visualize, but you can make an effort at that, I suppose. In practicality, though, what do? You don't typically look at the graphs like this after they get to past 2 dimensions there, the 3rd being the objective. You could do things like, what if I started at a bunch of different points? Right? I said gradient ascent was basically start at one point. What if I randomly threw out 100 points, had them all start walking up hills, let them all terminate, and then see which one got to the highest, right? Would I have a better shot of at least one of them getting on the big hill, essentially, right? That sound reasonable? Think of that as the intuition. I mean, I'm not the first one to come up with that idea. If I go to options in GRG nonlinear, what is this here? Multi-start. Population size, this is to me is I'm going to start in a lot of different places, right? Population, I'm going to throw 100 different spots on there I'm going to start with, and then I'm going to run it. Random seed, this comes from the idea of randomly picking those spots where I'm going to start there, right? Yeah. This is an option that you see it's not toggled on by default. You have to toggle it on. But when you're using the GRG nonlinear solver, you have the ability to tap into that, essentially. The other one that I will say is a way to combat this is evolutionary. I think in the first questionnaire that I give you guys in week 1, I say, hey, has anybody heard of things like genetic algorithms, right? Evolutionary programming is, I think, another way that people talk about that. That is another way to try this and combat this. If you're very interested in this, I'm going to give you a very quick snippet of it. But in the course resources, there's a series of lectures. It's a course basically taught by Patrick Winston at MIT. He's died a few years ago, I think. But basically, he taught a course on artificial intelligence. One of those lectures is on genetic algorithms. It's worth the 50 minutes watch if you're interested there. But basically, the whole idea of genetic algorithms, it's inspired by Darwin, essentially, right? And mutation, the idea is of the strongest things basically survive and recreate essentially at that point are all baked into that algorithm itself there. Whole idea is basically you start off with some randomness there. You basically have fitness functions. You basically evaluate who's the fittest of this population. You then get to pick them. Then there is this part that mimics recreation, if you will. Part A, B come together. They mix together. They produce some output, right? There's a mutation twist at that point. That mutation twist there is the thing that kind of throws the dice that allows it to scatter essentially across the surface. That's one evolution. You have that, or every evolution has 1,000 or so candidates, we'll say. You basically do this process, you get to the next evolution, right? So then you run that over and over again, say 1,000 times through 1,000 evolutions. Then you say, okay, what is the fittest thing? The fittest thing in our idea would be, what is the thing, since we're talking about profits, what is the thing that has the highest profit? We talk about these as candidate solutions in each one there. That is the idea that you can kind of have here. Examples of what you're seeing on the screen, convergence, how close do I have to be in order to make sure I'm good as far as termination conditions. You talk about incumbents, and we talk about things like the maximum profit that was achieved at every evolution. When it stops growing at a certain rate, let's bow out. That's convergence part there. Mutation rate. When these two things, we have, it's like when candidate A meets candidate B, they love each other, they come together. We're dancing around certain subjects here, if you know what I'm saying. Then they create a child candidate. That child candidate, we don't want it just to be copies of these. We're mixing them a little bit, but we also want to throw in a little genetic mutation, right? That happens with all of us, right? When we're born, there's a little twist there that God gives us. There's where I'm playing how much twist gets to happen here. You feel almighty and powerful here, right? You're acting as your God in your own little world, essentially.
It's like Neuralink's. I mean,
Neuralink's the thing from Tesla,
no,
or Elon, right?
I mean the programmation things, neural network.
Neural networks, maybe a little bit. The best close there is you're basically mimicking biology, right? To inspire an algorithm. Yeah. Same idea here.
Yeah.
Neural networks are basically very much figuring out what's happening up here, right, inside the brain, and trying to mimic synapses and so forth. This is more thinking not so localized to an individual, but through evolution of a bunch of individuals there. Population size, how many people are in each side of these generations or evolutions, randomness, bits here, and again, a termination condition there. Anyhow, fascinating subject that we don't have time to dwell on for an hour and 50 minutes, or else we'd get nothing done, essentially. Well, we'd have a good time, but well, we've got an hour, right? Yeah, we got an hour left. Let's hope so. I haven't even got to any examples yet. Who needs those? You guys are smart kids. You figure them out yourselves, right? All right. So again, hopefully I've talked to you at this point. I've framed your mind that, okay, yes, in some ways, nonlinear is very similar to what we have been doing. The modeling process that we've talked about is very similar, business problem to mathematical model. Yes, I'm going to be now having things that are not necessarily linear functions. I may have a quadratic type thing, but very close there. I then go to solvers. The solvers, yes, I've shown you, instead of GLPK, I've shown you IP-opt, and then we've talked about GRG, nonlinear, and evolution on the Excel side of things, as opposed to simplex algorithm there. Then I wanted to talk about the idea that not all these nonlinear problems are the same. That's why we introduced convex, concave, and then wicked looking things like this, essentially. Why is it wicked? We talked through that. And then talked about ways to combat the wickedness, essentially. That leads us to a couple of terms, and then we go to some examples. All right, some terms. Terms inspired by chapter 3 in my mind of this class. Chapter 3, we talked about sensitivity analysis, reduced cost, dual values, range of optimality, range of feasibility type stuff there. Now, there are somewhat of cousins of these things in the nonlinear space, but they don't necessarily look exactly the same. Reduced gradient is an example, similar to the reduced the dual value associated with it there. And so dual value is like shadow price type stuff there. So it is there. I'm not going to ask you much about it, but just know that that is a possible thing to look at. The gradient multiply is also the same thing. Rate of change of the objective function with respect to the right-hand side of the constraint. Yes, okay, that sounds like a shadow price type stuff as well. Big problem here. One of the things when we talked about dual values and shadow prices back in chapter 3 was that range of feasibility. You could extrapolate it, right? Begin within certain bounds there. In this case, those bounds are gone essentially there. Those bounds were defined by the linear nature of the model. In this case, it's nonlinear, so we basically have those set to 0 essentially. Again, just things to show you that are mapped to what we've talked about before, but will not be required from too much from you. Okay. I guess so at this point, I'll take a breath and ask how people are doing. Drinking from the fire hose, anybody need to go potty, anything like that? It's really what this conversation is at this point.
Wait, what?
Do we need a break for a bathroom break or anything like that at this point?
Yeah.
We good?
To eat that, but
You can eat while I lecture. It's okay. I can't eat, but you can. I'll let you. I left my dinner in the car. All right. So let's look at examples. These will be examples probably similar to what your homework set is, I suppose. 2 from finance, 1 from more launching a product type thing, maybe marketing type thing would be happening there, product management size. We've done a few different portfolio type problems here that's similar to what we're going to talk about in 8.2. This time we're going to create an index fund. I don't think we've done an index fund up to this point. The whole idea of an index fund in my mind when I think about investments is there's one line of thought that it's hard to beat the market. So let's just make sure we don't do worse than the market. We want to do similar to the market, right? And so that's kind of the idea of an index fund. You pick a broad market standard there, and then you say, okay, I want to build a portfolio that follows very closely to that market indicator, essentially there. When the market goes up, my portfolio valuation goes up. When it goes down, well, it's going down, but it's going down for everybody at that point. It's kind of the idea. This is nonlinear at this point, and so to give us some data to play with, I grabbed some stuff from NASDAQ. Here are these stock tickers for a few different companies and year-over-year performance indicators there. So Yahoo, Buffalo Wild Wings, Netflix, and Google, and I cannot remember who MU was off the top of my head. So we've got performance of a company in a given year. And we've got the performance of the index, the NASDAQ, over these 4 years. The idea is, okay, how would I build an index fund such that looking over the 4 years, I'm going to be investing certain amounts of money into these 5 different companies. We'll say we're buying stocks from them. And I want to buy it in such a way that for every year that I've seen here in this 4-year span, it follows as close to possible as these values here in the NASDAQ. So for instance, if the year was like 2009, I increased 35%. If the year is like 2010, I increased 15%. 2011, I lose a percentage. And 2012, I increase roughly 15% there. So that becomes a non-intuitive task, right? I'm basically putting percentages next to the companies, and I'm trying to make sure that all matches up here. What's the model look like for this? Well, I'll just show it to you here. And in one sense, that should feel like a familiar situation that I've described. We talk about sets, we talk about parameters, we talk about decision variables, we get down to the model, right? I've been trying to keep that cadence very familiar to you there, give you a scaffolding to work through problems there. In this case, we have year scenarios. That's the different years I've got, 2009 to 2012. And I've got investment options. In this case, I'm making them more generic. Instead of calling out these stock tickers, I say I1, I2, I3, all the way to I5 at this point. What data do I have? Well, I've got really two different types of data. One piece or set of data is the stuff in this table here, right? Stuff in this table is defined by a row and a column, so two different indices. One is the company, one is the candidate year. So that's what we're seeing here. We call it A, that's the return of investment for the option I in year S. Or no. Yeah, option I in year S. There we go. Market index. Market index here, well, it just has one subscript because all we're now going to do is capture the year of the index. And so I've got that as lowercase m sub s there. What is the decision points? The decision points is I have some pile of money that I want to invest in these stocks. How much money do I give to each one of those options, right? I haven't told you a certain dollar amount here, so we just keep it generic and say there's 100% of the money. 10% goes here, 20% this here, 30% goes here, so on and so forth, right? That divvying up is what we're after. Essentially, it's an optimal solution. So we say, hey, I need to figure out the fraction or the percentage of option I to be x sub I. Well, so what's the model look like? Well, the second constraint here should be the easiest one for you, probably of all. If I'm dealing with a fractional amounts of a total amount that I'm investing, we say basically we have to invest all the money, right? So all the pieces of the pie have to sum to 100%, or if I'm doing this as fractionally, I sum up all my decision variables, they must equal 1. We've seen all that before. Let's do this one here and work our way up to the objective function. Here, you can write this as an inequality there. I'm thinking of that more as a lumped variable. So I've got a return for a given year scenario there. So for every S and S, notice the S is the set of year scenarios. So for R of 2019, R of 2009, R of 2010, R of 2011, R of 2012. That's what this for every is meaning, saying R sub S is equal to what? It is the linear combination of the decision variables times the performance of that company during that year. That's what we've got here going on. So it's basically how would the portfolio perform in that year, right? Then it walks up here. Objective is to minimize some cost function. Now, cost function here, don't think of that as like profit, revenue and cost. No. Think of it as cost as far as an error term. You'll see that in other places, neural network type stuff. When you're training those, they'll talk about minimization of a cost function there in a lot of ways as you're trying to fit some nonlinear parameter. So think of this as a cost or error function. What am I doing? I'm taking the year scenario minus the index fund there. That right there feels like error to me, right? Because that year scenario, we want to be very close to the index. We want those to match if it was perfect, right? So we're saying take the difference of those and not add them all up right now, but first square them and then add them all up. What's the purpose of the squaring part there? Well, in one sense, if I did not square it, I could have a positive error on this side, a negative error on this side. They would cancel each other out. We don't necessarily want that, right? We want to look at the magnitudes of them. Okay, their magnitudes. There's two different options I can think of there, right? One, put the bars around it, right? The bars being the absolute value. That would give you positive values there, right? Why would I do squaring over positive values? I told you there wasn't much calculus now, but I'm referring to calculus, so forgive me, I suppose. What does the absolute value function look like? Does anybody remember on the XY plot?
What?
Looks like a V.
B, yeah.
A V, right? Yes.
Modulus.
The absolute value.
Absolute value. Yeah, it's
V.
take a modulus like.
No, just X and Y. X and Y, what's the absolute value look like? It looks like this.
Yeah.
V. What's a parabola look like? X squared looks like a nice smooth parabola. Which one's easier to take a derivative on? A nice smooth thing or a thing with a point? Points are not good. I'll put it that way. Points are discontinuous there at that point, right? That's the problem. That's why we like the squared part, easier mathematical parts there. So hence the squaring. Gives me the positive part here. And if I was to do things like ordinary least squares, yeah, I do dig into a little bit of calculus there. It's one of those tangential things. That's the last lecture. You'll see that as well. We don't go deep though. At least you're just you're snorkeling, and every once in a while I look down at the bottom of the ocean type thing. I can't help myself. You guys are the captive audience. If I don't talk to you guys, I got to talk to my wife about this stuff, and she just kind of rolls her eyes, you know. And then I got my partner at work. He looks at it and says this is satanic, you know. So there's a reason I'm here on Thursday nights.
It's better to get crazy, right?
Exactly. Yes, we all get crazy together. So that is the idea, the intuition there. We're minimizing the sum of squared errors. That's a statement referring to this, subject to a definition of the return on each year scenario. That's this right here. And then just a statement that all the bits that where I am investing have to sum to 1 because we're talking about fractional investments there.
What is the sign there?
What
It's
sign?
equal or it's
Oh, yes.
it's
The
equal?
yeah. There you go.
Equal.
Rendering on the projector is a little hard there.
Yeah.
Okay. I think I've talked about this. Nonlinear. Is it nonlinear? Well, let's see. Can we find anything wrong with this as far as from the linearity side of things? If I ignore the objective function, I'm fine. As soon as I look at the objective function, notice this r sub x is going to have some x's in here, and then I'm going to be squaring there. In very loose terms, think of the FOIL method, I think is what it was called at one point. First outside, inside, last, right? Think of that thing's happening. There's going to be some squared terms in there. It is convex, though, in the sense that, yes, there are going to be squared terms in there, but they're not going to have any cross terms there, right, as well. So that's good. It's going to be an easy problem is what I'm thinking here. All right, so how do you solve this? I'll do it in Excel for you guys because I think, again, most kids are doing it in Excel there. There's the Python side of things. That looks a little strange just because I'm using pandas and how I'm handling the data, essentially. But other than that, it's working very much like it always has there. All right, that should be good. So give me one moment to collect some data. Oh.
I envy so much that you can like just copy and paste go from
From the HTML.
yeah.
HTML goes straight into Excel. Yes, very nice.
Because every time that I need to do the exercise, I need to type.
Going from the book, yes, type.
Yeah.
Yes. Heaven forbid you fat finger a number and it's all wrong, right? Yes. We've all been there. I'm thinking in practice, though, hopefully, I hope to goodness if you guys are doing this in practice, you're not having to do stuff from a printed paper copy. Definitely press on the IT department. Hey, give me a CSV, give me something here, right?
Would be nice. Like you did on the last homework.
Yeah.
Mm-hmm.
Then on the exam, and I've gotten in trouble. And every once in a while, I'll get in trouble with that just because I'll change something in the problem and I'll change it in the HTML and not in the data set, and then I have to go give people partial credit or I have to grade it twice, essentially, depending on what they did. That gets me every once in a while. All right, so decision variables. Data on the left, stuff on the right for the model. All right. All right, so decision variables. I'm going to need something for an objective function at some point. Excuse my formatting. I'm not going to spend too much time on that. So we're minimizing. This will be the sum of squared errors. And let's talk about some constraints here. So constraints. First I want to do is I want to define these things. And again, I think of these as lumped variables in a lot of ways, just because the reason I'm developing these is so I can use them here. And so maybe I'll just put a little header here. And this is really R 2009, R 2010, R 2011, R 2012. These values here. All right, so what do we do here? For every S and S part, I basically have laid that out there. That's that part. Now for every one of these, what do I got to do? I got to do this part right here, the summation. What is that? That is a sum and a product inside the sum. I say that very intentionally to hopefully guide you to sum product, right? As the Excel function. I'm taking the vector, you could say, of the decision variables, and I'm dotting it with the corresponding vector, if you will, for the performance indicators. Trying to say that very carefully because I'm thinking in my mind two different vectors in the dot product and how that thing works together. Sum product for 2009 would be this and this, right? And then we do that a couple more times. All right. So we got some scenario returns here, but we also need to, now we got those R's defined. Let's go through the objective function. Let's get that first. R sub S minus M sub S squared, and I've got to do it for all the S's there. At this point, I don't really have a great way to do this, so I'm just going to type it out here. There's only 4 of them, so it's not that bad. R sub 2009 minus the index value for 2009 squared. That's the 2009 term, plus R of 2010 minus the index value of 2010 squared, right? You can see predictor kind of, let's say it's the predictor and the observed value, the difference, and I'm squaring. All right, so we have that. 2009, 10, 11, and 12. Just ignore the value at this point. What's in there? Then what have done? I've done this. I've done this. I need to hit this. Usually I would write this as something like this before, left-hand side, right-hand side. It's an equality. And this is investments sum to 100%. This is the intuition here. All right. At this point, I think we've done all of our worksheet work. Come to the solver. Set the objection. That's good. Objective. That's good. I want to minimize it, not maximize it. Allow it to change those decision variables. Now, this is the slight little difference when I'm talking about lumped variables. I don't necessarily need to put them in here. Basically, they're convenience mechanisms. Why do I say they're convenience mechanisms, you may ask? Notice this R variable itself, I can replace with all of this, right? So conceivably, I could eliminate this entire line by sticking this expression every time that I see R sub S. And I would have the same mathematical model. Would that become very convoluted and be hard to read, essentially? Yes, it would. That's kind of why we have it introduced the way that we have, but it's not really adding any additional new information to us, right? It's a convenience mechanism. With that being said, I don't think it would hurt if you loaded these in there. Make unconstrained variables non-negative. Yes, I don't want these to go negative in terms of the decision variables. And GRG nonlinear is fine. I think it is one of those nice, smooth, objective function surfaces that I'm trying to traverse, so I'm not worried too much there, and I'll just hit solve. Yeah.
you are putting the variables in square, you said that we are not going to have negative values. So why it does matter if we have or not negative values on decision variables?
Oh, yeah, two different things I think we're talking about here. One sense when I talk about the square here, right? That's what you're talking about?
Yeah.
Here I'm talking about the error that's basically generated by that year candidate minus the index there. I don't want 2009 error to cancel out in any way 2010 error, right? That's why I square each one of those. That's that part. So that's that statement of error and why we're squaring it there. The other one though is, I think you're talking about this bit here, make unconstrained variables non-negative.
Yeah.
I don't want the solver to even entertain these values going negative. That doesn't make sense, right? Here I'm trying to pay out percentages. I'm not saying, okay, the portfolio is going to give me money and then I'm trying to invest that. That doesn't make nonsense. That's nonsense there. All right, and what would it be? Okay, so we solved it. There's basically your breakdown of what you should, how you should allocate your funds is the way I should say that. MU receives, let's say there's $100 you're investing. MU gets $4.76. Yahoo 72.3. Buffalo Wild Wings 15.72. Netflix 7.22. Google 0. There essentially is the way it's describing. This yellow value here, this is a description of the sum of squared errors. It may be better to look at these values here and these values here. The whole idea of the index fund was pick values here such that this matches this fairly closely, right? Let's see what happens. 35 and 37, pretty close. 15 and 14, roughly, pretty close. -1, -2, pretty close. 14.8, okay, 21, slightly bit more, but 3 out of 4 we did very, very close there, right? And so that's the idea of that index fund happening there. Last constraint, 1 = 1. Yeah, we're all good there. Python side of things, yeah, same solution there. So there you go. Creation of an index fund.
Do you use that in your personal life to?
Not yet. I haven't really got into the stock side of things. Every year I talk through these lectures and I do ask that same question. Why am I not? Essentially, at times.
Because it's something that I asked to you a few classes ago. So I can use it and said, "Oh, you are asking me if you can apply what I've in your daily life?"
Yes. No, that's one of the beauties. The reason I've chosen to teach this class is the fact that so much of this stuff is applicable, immediately applicable.
Yeah.
You don't have to go to work. Like the problem being, if I go talk to you about heat transfer, in mechanical engineering type stuff. If I'm building bridges, I don't typically work with heat transfer stuff, right? In the electronic space that I deal with, lighting fixtures like this, yes, you worry about heat transfers. You have COBs that have certain temperature tolerances to figure out how much light comes out over a given amount of time, right? That becomes a thing, but it's a niche thing as far as that piece of knowledge of heat transfer is niche to that industry essentially there. What I'm teaching you in this class, very broad. Very large set of industries can be applied here, right?
Yeah.
Problems will vary as far as what they look like, but the mathematical fundamentals can be applied there. Yes. This would be a use case, yes. I was texting last night with my mother, actually, and I made the text of, it's tax season. I'm interested in a lot of mathematics. Taxes is not one of them. So I just pay somebody and say, I'll pay you, and I don't want to think about it. All right, so if we're all good with the index funds, we're sitting at 6 o'clock. Yes, we're on good on pace to get out of here, yes. All right, so last time we talked about the index fund. Again, the index fund, the goal. I want to match the market, essentially. Other times we don't have that as a goal, right? We want to maximize our return, minimize risk subject to a constraint on the return, those type of things, right? That's where the Markowitz mean variance portfolio model comes to play there. And it's really trying to balance these things, balancing risk and balancing return. When I talk about risk, when I talk about return, I have to then be able to quantify those to perform the mathematical model, right? So that's what the first few bullet points here. In the Markowitz model, when I say return, think of it as the expected return. I think we've had the word expected in this class from the probability sense, right? You have a set of outcomes, they have certain values tied to them. They have also certain probabilities that one of those outcomes is going to occur. Hence, you talk about the expected value of that system, right? The lottery is a big thing there, right? If you compute the expected value of buying a ticket, it's going to typically be biased in the state's favor. I say typically because I've got a book at home that's called Humble Pie, written by a mathematician that's also a comedian. I'm pretty sure that they talked about one instance for one state. They got that wrong. And essentially somebody took advantage of that. Anyhow, good book if you're interested in such things. All right, so expected return, R bar here. We have return scenarios. That's the same idea that we just implemented with the index fund there, but now we have to have an additional bit of information, right? The probability that scenario is going to occur. That's the piece of S value there. Easiest case scenario, you say you have 5 different, we'll say, year scenarios, and you say they're all equally probable, so it becomes 1/5, and you get to move it outside of that summation there. So that's how we talk about return. What about risk? Risk, they talk about in terms of variance. Again, coming back from the probability landscape there, you may have seen like normal curves, and you talk about standard deviations and the variance there, right? That's kind of the idea is to be thinking about. In the variance there, if you're not really big into probabilities, think about those normal curves, and are they very steep and narrow, or are they very kind of short and wide, right? One has a big variance, one has a narrow variance there. So that's what we're talking about here. And so what do we have? We have the probability of a year scenario. We've got the return of that scenario minus R bar. So now we're seeing kind of this spread away from the mean, if you will. And then we're squaring it. Similar ideas there, I believe, as far as summing squared errors. Essentially, it looks like the cancellation type of topic there. And we have an expression basically for variance. In a nutshell, we have returns defined by the expected return. We have risk defined by the variance. And we've got relationships to describe each of those. So there's different ways to describe the model then at this point. 2 fundamental things is minimize risk by setting a lower bound on the return. That's the first sub-bullet here. Or I maximize risk and set an upper bound on the variance. Actually, maximize return, so upper bound on the variance there, right? In one sense, you're maximizing something and putting a ceiling on the variance. In other things, I'm driving the variance, the risk as low as possible, and I'm setting a minimum on the return. So let's go with this part here. I will maximize the return subject to a constraint on the variance. What's the constraint on the variance? I want to maximize or have a maximum or a ceiling set on it so that the value is 30 there. Again, I think we're talking about year-over-year returns there. We need some probability information. This is kind of the easiest way to say it. Assume each one of those year scenarios is equally likely. 5 years comes out to 1/5 or 20% in each one. And there's the nice little markdown table. So what are our options here for investments? Well, that's that first column. Foreign stocks, intermediate term bonds, large cap growth, large cap value, small cap growth, small cap value. Definitely sounds like a lot of stuff that you see with like 401k type stuff. There's what comes to mind. And then I've got different year scenarios there. So we've talked through this in terms of casually what the model components would be. So now just to show the model down here. Again, I try to very much emphasize this idea of a framework that you can walk through these problems with. So we talk about sets, parameters, decision variables, then get down into kind of the heart of the model. Sets, I've got year scenarios S and investment options I, same thing that we just used for the index funds. I've got return investment of an option I in a year S, same variable I used before. Introduction here of a probability of a scenario. That's a little bit new here. That's the piece of S. Decision variables are still the same. I've got to figure out how much of my capital I'm going to divide into these investment options. So X sub I there. Hence the model. The problem said I'm going to, where's the mouse? There's the mouse. Maximize return. Well, return was defined by R bar here. Hence, we just say maximize R bar. Okay, very well defined. Subject to what? Well, just like last time, I've got floating these R sub S's around here. We talked about those as a lumped variable just a little bit ago. So I still have to define those. So this line right here is the same as the index one. Well, from these, I got to define the R bar. So that's what I've got here. Again, that's kind of acting as a lumped variable because I've got that referenced here as well as here. And then I've got investment unity. That's the same as last time, right? Just same argument. I've got some amount of funds. I want to invest all of them. So I got to sum to 100%, if you will. And then down here, I've got a ceiling set on the variance right there. The maximum variance is set to 30. Well, what was the definition of the variance? The definition of the variance is right here. And we just set a ceiling of 30 on that. Hence this line here. And then the non-negativity here of all the investments, opportunities must equal, or must be greater than or equal to 0. So hopefully, yes, that looks potentially a little intimidating. Hopefully you guys have started getting used to this form of mathematical writing there. Trying to think back through the survey questions. I think there's usually a mixed bag. I think this class was about the same of a few people are relatively comfortable. Some people know some of the letters. Other people are like, I don't know what you're talking about. That's typically the way that survey goes there. But hopefully as I talk through these things and you look at them, they start becoming more and more familiar. No, they don't look like the things that you typically write your name on as far as when you print them, but they grow on you over time, right? All right. So now we run it. If you want to play around in Excel here as well. Yeah, we'll grab this table. Should be able to copy and paste from it just as same. Got some nice. Yeah, that did turn over. Ooh. I really don't want that to be wrapping, so blow it out a little bit. That's good. And yeah, you guys should say that pretty good. So just the data section. All right, so the model, we need decision variables. We need an objective function. We are maximizing the expected rate of return. Subject to some constraints. What was the thing we did first last time? We had year scenarios and we had to come up with the candidate returns there. Here, these are all vertical. What is it? Paste transpose. Can I do that? Oh, look in there. So this would be that sum product, right? Kind of the top product in those two vectors, linear combination, however you want to think of it there. So this and this. Here we're defining the R of year one. That just to make sure we're all clear, I'm defining these at this point, the R sub S's. Same thing we did in the index fund. Yeah, I messed something up there. There we go. All right, so these are the R sub S is defined. I need to define R bar, and I have to use it in a couple different places, right? Once here in the objective function, once down here in this variance calculation as well. So R bar is what? It's going to be a single cell. So I'll call it R bar here. And it's this bit right here. What's that say? Take the probability of every scenario return, year scenario that is, and multiply that by the year scenario, and then add all those up together. One way to think about this is that the probability P sub S is going to be the same number for all these things, right? We said they were all equally likely. There's 5 of them, so that's 1/5. That's 20% essentially. So I can pull that outside. By outside, I mean I can, since that is a constant, I can pull that out here and say it's the probability of scenario times the sum, and I'll write it like that. So there's 1/5, or it's 0.2 times the sum of all these. Again, if that was not a constant, you would have to do that as like a sum product type thing, which probably is how you do that in Excel. It would be more specific, and you would have like probabilities out here of each one that you would be forming it on. We said the objective was to maximize R bar, so I'm just going to put that there. So again, I kind of think of these as lumped constants or lumped variables would be probably a better way to say that. And then I've got a couple constraints here. Investments sum to 100% was 1. And we're setting a max variance. All right, so I got to calculate variance. What is variance? Again, that P sub S is a constant, so I can move it to the left of the summation, right? So that simplifies things. And then after I do that, then I've got like this sum of squared errors thing happening there between R sub S and R bar. So let's go about that. 0.2 times the sum of R sub S and R bar. So there's like year 1 minus R bar. Ooh, minus no. And that, I wouldn't do that.
It's possible to put the objective function as a constraint.
No, that's why I hesitated there. Yeah, I put R bar up there and I was like, oh, better not. No, that's the objective function. It's going to want to play with that value.
Okay.
So we put that here. Yes. I caught myself there as you were questioning it as well. Like, oh, no, that didn't feel right. All right. So plus year 2. This is the R sub S minus R bar squared plus year 3. R bar squared plus year 4 minus R bar squared plus year 5 minus R bar squared. Then all those in parentheses because I'm multiplying them all by 0.2. Okay.
Wait, the objective function is to maximize the R bar.
Yep.
Kinda, you are putting the R bar as a constraint.
I am using it as in a computation of a constraint, yes. And yeah, I believe I've got this big header on constraints, but here's where it is. Like I'm not going to load that into the dialog box of constraints there. I just want to cell here because I need to put it here, and I also need to use that here. You can actually see that if I go here and trace dependence. I don't know if you've seen that before in Excel, just be able to see the references visually. All right, so we wanted to maximize the expected return. We need to tell it where the expected return is in the objective function. I want you to play with these cells here. I want you to make sure when you have the objectives that they all sum to 1. This. And I want to set an upper bound on the variance. All right, make unconstrained variables non-negative. Yep, still like it. Just hit the GRG nonlinear solver, sounds good. And we have a solution. Solver found a solution. All constraints and optimality are satisfied. So that's good. So again, these are basically percentages. We'll wait to look at that. It's kind of a percentage there, expected return. Oh, no, that is not a percentage there. The reason I'm formatting those as percentage, those are floating point decimals, right? That I can think of as percentage multiplied by 100, I get a percent here. These values here are returns, came in as decimal values, positive, not decimal values, greater than 1 essentially there. So do not multiply those by 100 there at this point to get percentages. All right, quick check here to make sure we're agreeing on certain things and are on track. 10.45 expected return, that looks good. Investment strategy, 13.28, 49.55.
What is my percentage on our Excel file?
Here?
Yeah.
These are actually,
In your Python code, you found the answer in percentage.
here?
Yeah, like expected return 10.45%.
Hang on a second. Yeah, a little bit different here as far as what we're talking about. Here I've got candidate returns, and those candidate returns are kind of come from these R values here. And so those are stipulated from the data sets here, is where they're driving, right? Notice these, like this is interpreted as 10.06% at that point.
Oh, they are representing percentage.
Think of those initial ones as percentages already. Whereas these, the raw value that's going to come out of the solver for that is going to be roughly something that looks about like that.
Yeah.
So that's where I'm just formatting my decision variables in Excel as percentages there. If I don't do that, then they're going to be floating point numbers. If I put that like to general as the data type, you would see that.
Oh yeah, like the other ones, it's like if you put percentage, we will change the value.
Yes, depending on how you do that in Excel, you're mostly adding 2 decimal places there. Yeah.
That's because of a lot of points lost on the way, you know?
Yes, that can be an issue. All right. So again, it's a fairly simple problem there in the sense of computationally. That's a nice problem to have. If you go inspect it again, you won't find any of those little devilish tweaks in there that cause things to have local optimal, local maximum minimums there to get trapped up on there. So I guess before we go to something a little more nasty, any questions, concerns on Markowitz?
Time to ask questions now, right?
Yeah, if you want to, yeah.
Okay. Now I still don't see how can I do it myself. Do it by myself, you know? Like, how can I form the statements that will lead me to the Excel configuration?
Yeah. So the problems that you'll be given are going to come from 4 different places I can think of. One of them are going to be like the first one that we talked about tonight, which is more like you're going to have to figure out the mathematical model. That's going to be one sense. The other ones, they'll be very similar to what I'm talking about. Like the question will say, create an index fund. If it says create an index fund, your mathematical model is going to be looking like this. So just format it into that. If it says, hey, you're going to work on a Markowitz portfolio model, it'll very much follow this. This definition will be the same. That definition will be the same. The only tweak is there's 2 different ways to run the Markowitz defined there. We basically did that one. I don't exactly remember what I told you on the homework set, but it could be that one or it could be the one right above that. There you're just flipping where are you putting the variance, where you're doing with the expected return. Other than that, they stay the same. The other alternative that we haven't talked about yet, and I believe there is one on the homework set as well, is this forecasting with Bass forecasting there. So in one sense, I'm basically presenting 3 different very well-known mathematically defined models index, Markowitz, Bass forecasting will be here. Then there's a fourth little bit there that's like you come up with the model. And that's the same exercise that you've been doing basically since chapter 2, essentially, where you're having to read a problem state. Okay, what's the decision variables? What's the objective? What's the constraints there? Make sense?
Makes sense.
All right. So, in all honesty, now we get to the point of the lecture that makes me a little more nervous. This is what kept me up a little bit last night, to be possibly saying at one point and muttering a choice word or two on the couch when everybody was asleep. All right. So, the problem that we're looking at from the business perspective, it is a somewhat challenging problem to introduce a new product. Specifically, introducing a new product and being able to accurately forecast the demand of that new product, how much you're going to sell in the first week, how much you're going to sell in the first month, how much you're going to sell in the first quarter, right? Those are things you want to know as far as if you're having to tool things up as far as, hey, I've got components that I'm going to use specifically for that product there. How many do I need to buy so they're ready for day one, right? Worst thing you have happen is, two bad scenarios could happen at the very beginning. You buy a whole lot of them, and then it does not sell hardly at all. So now you got a bunch of inventory you're sitting on that is not going out the door very fast. That's a problem. The other problem is you buy very little, it sells like hotcakes very quickly. You run out of the component. Now you have to tell people, hey, sorry, we'll accept your order, back order it. It'll be 3 weeks. Depending on the product, they may say, no, cancel my order. You've lost business at that point. So the reason why forecasting matters, right? This actually does happen as far as the ideas of this. I've actually written a dashboard within the last couple of years where basically it was a justification thing and basically said, okay, it plotted over time. Here's the forecast. Here's the actual bit. How close were they? Essentially, there was the argument that the people were making. Well, that's a tool that could be used in this is the Bass forecasting model. Okay, it's relatively young-ish, we'll say. It's going to turn 60 within 3 years there. So what is the idea? You attempt to forecast the model, forecast the adoption of a product after it's introduced. Okay, that's the problem that I was just describing. It becomes nonlinear. It's a messy nonlinear one. And we have these 3 different parameters that I'm trying to estimate. So when I say parameters I'm trying to estimate, I'm running a solver. I want to come up with the values of these things. These are M, P, and Q. Those are the letters we'll use for it there. Think of them as decision variables, if you will. M, you basically are trying to have an estimate of, at the end, how many people are going to buy the product, adopt the product there. That's useful to know, right? Am I thinking this is going to be a product that has 100 people that's going to be interested in it or 1 million people that are going to be interested in it and actually buy it, right? A good thing to know. P and Q are going to be talking about factors that would influence their decision to adopt/buy the product. Q, coefficient of imitation. Think of this as word of mouth. I buy the product. I'm talking to you about the product. You hear me talk about it in a good light. You buy the product, right? Those 10 show areas happen. That idea is Q, coefficient of imitation. Coefficient of innovation, I don't talk to anybody. I discover the product on my own. I'm interested enough about the product by itself. I go buy the product there at this point, right? The individual's own interest is driving their adoption of the product there. Those are 2 very isolated things, right? At one point, I'm influenced by another. Another one, I'm basically just influenced by what I see and understand myself there. So 2 influencing factors that we're combining together. This comes together in a adoption likelihood. So think of it as the probability you're going to be adopting based off of the number of people that have adopted at the previous time step here. Capital C, when you think of capital C, think of that as a cumulative value. So I'm talking about cumulatively at the time step before that I'm currently sitting on. That's the T-1 part. How many people have already adopted the product? Then I come up with this likelihood. What's the likelihood given the things we just talked about? Well, P, think of that as a probability that you're going to buy it on its own. That's the coefficient of invitation. So it makes sense that that's by itself. Now look at this product over here. Q times the ratio of C to the M, T-1 divided by M. Let's look at the ratio first. C to the T-1 divided by M. That numerator is how many people have already adopted the product in the previous time step divided by the total estimate of the amount of people that are going to ever adopt it. So now I'm at like the fraction of people that are going to adopt it That's the ratio. And I'm multiplying that by a value that talks about this word of mouth interaction, right? So that makes sense. That would be influenced by how many people have already bought it, right? It's intuitive reasoning here. And so I'm combining these things to get the adoption likelihood. Now we have this expression. This is my forecasting method. Tying it into earlier in the lecture, this is similar to the gradient ascent thing I showed you. Yes, the gradient ascent thing had the ugly gradient or very beautiful gradient, however you want to look at mathematics in some ways. But it was basically iterative. I was at a point in time, and now I'm going to the next point in time. The gradient, I was at a point in space, and I'm going to the next point in space, right? That's what I mean by iterative. So in this case, you'll see my forecast at some time t is related to the cumulative amount of people at the t minus 1, at the previous time step that have adopted the product there. And then you can see everything else here. Another thing to think about this is if you look at it, this first set of parentheses here, what is that? That is exactly the adoption likelihood. So I'm taking the adoption likelihood and I'm multiplying it by what? M minus c to the t minus 1. What does that represent? That's the mean of people that we think that will eventually adopt the product that haven't yet, right? So hopefully I'm talking about this in the way that it somewhat makes some intuitive sense. The model, again, a well-defined model. This is something I'm sure that was published by Mr. Bass long before I was born. I'll be able to say that, thankfully. It looks like this. What do I have? I have sets of time steps. This is getting a little bit of the time series analysis that we'll see in our last lecture, T1, T2, T3 to the end. I'll have a forecast value for time t, that's f sub t, lowercase, and I'll have an error term. Lots of error terms tonight. So e sub t. And we'll have a sales revenue s sub t. That's the revenue at that given time step as opposed to the cumulatively, which would be the cumulative nature up to that time step. What am I doing? Hey, looky there. This is a common thing. You see this a lot. Describe to me this objective function. Okay, drill into cost. What does cost mean to you in that statement?
The cost, like cost, not like financial cost, like.
Right. Yeah, keep going.
Keep going. Okay. To minimize. What is E?
Okay, jump down here. Here's E.
E. Oh, the error.
Yes,
Yeah.
yes. Minimize the sum of squared errors again, right? Yes, it's a popular thing. Yes. So minimize the sum of squared errors. That's happening here. We've talked about why it's squared errors, right? Not the absolute value. We've talked about that kind of stuff. This is common. We'll see a minimize the sum of squared errors again in the forecasting method there. I think it's also in ordinary least squared. It's been a while since I've looked at that, but I'm pretty sure it is popping up there. Subject to what? Well, let's jump down here. First, we have to define an error term, right? It's the objective function. Well, the error term is what? What is this statement? Take the forecast, subtract the actual value. That difference is error. Makes sense. What's this line here? Well, how are you going to calculate f sub t? Well, right there, it tells you exactly how to calculate f sub t. Here, m greater than or equal to 0. My argument here being m is the estimate of the total number of people that are going to adopt your product. That can't go negative. On a very bad day, it could go to 0, right? You spend a lot of time and effort and money developing a product and absolutely nobody sells it. Not a good thing.
Yeah, but like that number cannot be negative, right?
That's the point. Yes, that's why we're putting that constraint on there. Okay. Yep. It can be 0. Very bad day if it is 0.
I mean, that operation cannot be negative. I mean, m minus ct minus 1.
Yes, then you'd have a forecast of a negative. Yeah, I agree. That won't fall out as negative. Yeah.
That cannot be negative, right?
In intuitive sense, yes. If you had m to ct minus 1, if you had that thing go to negative, I have to think through that a little bit. If this is negative, but this c sub t and m is also right here, so Positive, negative. Yeah, it shouldn't be, I don't think, but I would have to play around with this a little bit to see if there's any possible way that that could become a positive value for S and T, is what I'm thinking. Can I come up with a solution there that happened there?
Because, for example, n just need to be greater or equal 0.
That's an independent constraint that we're applying, yes?
Yeah, but CT can be greater than 0.
Hopefully is greater than 0, but could not become less. CT is basically talking about the amount of adoption you've had up to the time just before you're looking at it in your time step there.
Yeah.
Yeah.
So it's a natural number, right?
Yes, I believe it. I'm hinging on the definition of natural, just to make sure we're agreeing there.
It's like an integer value and non-negative.
Oh, okay, yeah. I see what you're saying there. I don't know in this situation, depending on how you calculated adoption, like in this case, I think we're going to make a proxy of adoption being revenue dollars. Then you would drop off the integer requirement there.
Okay.
But I think we're on the right line of thought there. I think we may be getting tripped up a little bit in the details there, a little bit. So I wouldn't dive too much into it to say, okay, MBS has to be greater than or equal to 0 because I can't go in the opposite direction there. I can't have a negative adoption, we'll say. Yeah. So to play with this a little bit, we have to have some bits of information to get going here. And so that's what we've got here. As a proxy of adoption, we're going to talk about a film, and we're going to look at weekly revenue there. And I believe this will be in millions of dollars is what we're thinking here. So this is the data sets you would be given. Here, ma'am, looked at the first 12 weeks of a similar type of movie, and I get this result that's happened there. And maybe the idea is I'm going to release this movie. I've got a similar movie that's about to come out there. Can I look at historical data on that one to estimate what's going to happen with this one, essentially? Think of it that way. I've got weeks, revenue, and cumulative revenue. So really, the only independent variables is the first two columns. The second or the third column can be derived. What do I mean in the third column is derived is you can basically say and lock B2 and come up with those values, right? It's cumulative in nature. This is the sum of everything that's gone before it, essentially. All right, so there's the data set. Now we need to basically run this type of model in order to figure out MP and Q. So what do we need? Well, we've got cumulative values. That's already defined here. We need to figure out forecasted values and error terms and error squared terms. So what I would suggest doing is I would say the same thing like I need a forecast column, an error column, and just for making it easy, an error squared column. So let's start here, for instance. The error is what? Forecast minus the sale at that time step. So forecast minus the sale at that time step, not the cumulative, just the regular one. So that's why I'm going to column B there. Well, error squared is simply error squared. So we have that. Now, if we get over here, we got to implement this. For every time step T, implement this. Okay, this is good as long as I can take one step back, right? t minus 1 in the C. What if I'm at the first step? Then what happens? I can't step back, right? There's got to be a way to start this thing, right? A way to prime the pump, if you will. Well, in this case, think of that t minus 1 here. If I'm at 0, I can't go to -1, so we just drop these terms. So 0 here, 0 here, I end up with p times n. Again, following that kind of FOIL methodology. Now that I have week 1, week 2, I can follow this formula directly. So this is equal to P plus Q times C sub t minus 1 divided by m times m minus c to the t minus 1. All right. Everything in row 2 I need to lock. Okay. All right. We need an objective function. We haven't put that in yet. Minimize the sum of squared errors, right? We'll minimize the sum of squared errors. All right, save the file. This thing did crash on me at least once last night. So when you know you're having fun. All right, let's see what happens. We'll go to data, solver. Set this here. I want to minimize the sum of squared errors. I want to apply that here. And if I look at this, that's all baked into there. This is all baked into here. M is greater than or equal to 0. Okay, so in one sense, I could just hit solve right now. So let's just see what happens. All right, not too surprisingly, we end up with errors here. Okay.
This is from here.
Oh yeah, familiar pain point, right? I've been here, right? And so you start playing around at this point as far as, yes, okay, that's unfortunate, but I do know it's a harder problem. So what if I seed it a little bit here? What if I just put 1, 1, 1 there? I'm not going to change anything else. I hit run. Hey, it didn't error out there, right? This is Excel being finicky in my mind as far as what it's doing. So it does find a solution. Okay, it got a solution. How do I know if that solution's any good at all? Well, I did it before, so I know that. But besides that, this whole thing is developing a forecast. And so for these BAS forecasting models, the idea is to create a curve, we'll say, that will be similar to this curve. This is the observed data, this historical data, stuff we've watched. Let's see what our model does. Still, it would be week 1 through 12. And we'd look at that forecast column. Why it does that right there drives me nuts. There we go. Well, does that look good? Well, I guess if you're making a mountain, maybe, picture, that looks good. But no, the orange line is supposed to go close to the blue line in some way, shape, or form. And now it's all zeros, right? That's not good, right? So we have to play some more. And so this is where you start saying, okay, how do I play with this a little bit? Well, I'm going to go ahead and remove these. In one sense, you could think about starting this at a little bit there. Okay, that didn't work, right? You're just picking values. In one sense, if you weren't in this class, you could just start picking little values here and see what ever gets to you. But I did mention that the recognition of this is a hard problem, right? Well, I don't want to do gradient descent type stuff there. Maybe I need to get a little more complex. And so let's go to the options. Maybe the first thing I do is go to GRG nonlinear, and I go multi-start here. Let's leave it at 100 and just see what happens.
You found the problem that is like finding the local peak.
Yeah. Or a trivial thing. Yes, that's what we're running into there a little bit. Okay, now it's saying, okay, if you're going to do this, you have to have upper and lower bounds on your variables. Okay, so I'm going to make it happy a little bit. P and Q are thinking of probabilities, so I'm thinking less than or equal to 1. So let's see if I can put that here. That's 1. That's another one. That's good. M.
Can't you just select all of them and put less equal to 1?
I could have done 2 of them. I'm not gonna have 1 as the other one. The M I'm expecting to be a bigger value here. I want to make sure I throw it way up there, essentially. The other ones I'm picking 1 because I think of them as probabilities, 0 to 1 right there. The other one I don't. It's talking about millions. It's 100 million, 1,000 million, billion, right? You know. So I'm gonna pick something like 100. I believe that would be like 100 million at this point. And then I would become skeptical if it did hit 100, right? Because then I could have upper bounded it, artificially killed it. So if I ever saw that, I would increment it higher there. So let's see this, unconstrained variables non-negative. Let's go there. Do we have multi-start going? Yes, we do. All right. Whoa, what happened? Very different results, right? It did take a little bit of time. Also, you probably cannot see it very well. Let's run it again. I want you to focus here in the very bottom corner here. It's hard to see from the screen, but sheet 1, sheet 2, sheet 3, and then underneath that, you'll see some numbers. They'll start popping up here when I hit solve. See the little bit down there. It says incumbent, problem, and some other stuff there. This is where I'm talking about as far as throwing the dice on the field, letting it run. It's running there all chasing their own subproblem. That incumbent, it's like the best value that's found in a given point in time. It's keeping track of that, and then seeing if it can terminate, essentially. Notice even the statement here. Solver converged in probability to a global solution. That just shakes with confidence, doesn't it, right? They're saying, yeah, I think I got there, right? I can't be guaranteed, but I think I got there, right?
The whole confidence that I need to answer your exam, right?
Yes, exactly. And so this is just some of the nature that I want you to appreciate as far as linear programming. There was confidence there, right? That thing solved, you knew it exactly. I'm at the global solution. Nonlinear, you don't have quite that confidence, right? In this case, yes, I believe this is very close to what I've seen before there, and that's the way I'm going to see. I'm seeing those graphs. Yes, that thing did pick up the curvature of that. The first step here, yes, I had to artificially increase that step there. There's a little bit of increase there, so that's fine with me. And then I have this general hump and then decay essentially happening there. That all makes me feel pretty good about that. I was able to, the model whole idea here was to estimate these parameters. So this gives me idea of coefficient of imitation, I believe, and innovation there, remembering back to the definitions of P's and Q's. Yep. And then an estimate of the total number of people. Again, I think this is like in millions if you read the actual problem statement there, but you end up with that result there. We could also do this a little bit on the evolutionary side of things. Just for kicks, we'll see if that gets me a good result as well. So you can go evolutionary down here. Again, if you look down here in the bottom left, you'll see some stuff happening here. We'll see what it does. That happened very, very quickly, almost too quickly. There we go. The fact that I had those ones there kind of seeded it there. But in the bottom left, you know, you see the similar things. Incumbent, sub-problem, trial solution, objective cell. It's sitting here 4.496, so it's like at a certain timeout, I think. Like if there's so many seconds or so many evolutions it'll take. If it doesn't move off 4.496, it terminates there. You can, I don't know if you can hear it, but the fan on my CPU just kicked up a little bit here.
Yes. Yeah,
So,
it's possible to hear that.
yes, it's working a little bit here. At this point, we've already solved the problem, so 4.496 is already what it's going to be terminating at. It just doesn't know that yet at this point. So we'll let it burn. I mean, this is piped into the electricity of PSU. Your tuition dollars are right now funding this operation a little bit, you know. Somebody else's tuition dollars are going there, right? And there we go. Very similar result, 34.07.49 there, essentially. That's very close to what we had before. There's same overall shape between the two of them there. I do think in the homework set I'll check here, but I think you may be doing something similar to this and actually having to send me the graph. Basically send me a graph, something like that. Do label the axes and the series there. I'm being lazy and I've got 10 minutes to get done. So, forgive me for such things. How do you do this in Python? The way I did this in Python was I basically mimicked multi-start myself, essentially, slightly doing it from scratch. That's what this bit of code is here. Basically, we talk about like building out and testing different starting points, if you will. That's what that nested for loop is doing. This is kind of like we talked about 2 different dimensions. I could plot it visually. Now I've got three different decision variables, right? The M, the P, and the Q, right? There's a 3 there, so that's why there's 3 different for loops there. And then for every one of those combinations in these ranges, this is testing 0 to 100 in 10-step increments. This is 0 to 1 in quarter steps, 0 to 1 in quarter steps there. Then I build the model out. I solve the model out. I say, okay, did it say it's optimally found or not? If it's not optimal, just throw it away. Who cares? If I haven't found a best objective yet, well, it's got to be the first time I found it, so let's store that. Or if there is a best objective and it's going to be beaten by the model, I want to replace it, basically is what happens there. And I end up with values pretty close to the same. It does also take a little bit of time to run. This little bit here says keep track of the time that it takes. Well, that cell took roughly a minute to run, very close to 50 seconds, we'll say. And you end up with something similar to this-ish. Get the same? Rise and fall is really what I'm looking for there. This is closer to what I would expect from you guys. From a homework problem situation, you can do in Excel. You don't have to do it in Python, but just the idea of a title, axes titles, labels for the observed, which is the historical is what I call it here, or forecast or model one there. But yes, just understand there, out of the ones you have, if you have a BAS forecasting one, that's the one that you're going to be playing with a little bit as far as tweaking things around, kind of like I was playing with there. You saw the first effort when I didn't go into multi-start. What did it tell me? Excel just threw up its hand and said there's some error here. Then I put, I think, ones in there just to kind of seed the first thing. What did it do? Came to the trivial solution. Just put them all as 0, right? That obviously is no help. So then we move on from there.
If I understood the reading of this, like the forecast is how much you expect to sell, or for example, adding a new product, you expect to sell this amount of products, right?
That's the idea of a forecast, yes.
Yeah. That's good. I don't know the word.
The English word, yeah. Forecast is this, prediction of future events. Think of it that way, yes.
Okay. And historical is the
Observed. Yes.
So how much was sold?
Yeah.
Okay.
So in this case, think of it very much of that historical one may be like a very similar movie that you've already released years ago. Mm-hmm. And this one falls in that same line of thought as far as, okay, can I fit a model of the old one to then use that model on the new one to see if I can start figuring out exactly what's going to happen there? Okay. So with that, we've reached the end of our nonlinear discussion. Congratulations. Maybe we should get t-shirts for this class at some point, you know.
How many chapters we are going to study?
You're over halfway.
Yeah.
1, 2, 3, 4 left. I know, it goes fast.
Yeah. We only have 4 chapters to go?
4 more lectures, 2 more exams, including the final.
I thought we were about to have like 18 more.
18? 8 more.
8 more.
We have 1, 2, 3, 4, 5, 6 weeks of school left after this week. Yeah, not much.
Oh, so the last one would be the 80th one would be the final exam.
Yes. And I think here is actually there's a week right here of dead week that we really don't do too much in this class. The idea is you guys finish up, start working on the final exam, ping me if you have any questions type thing.
Yeah.
There's an extra credit problem that I usually give out to the people who also have the ability to work on that. So with that being said, chapter 8 homework, usual stuff, opens now, closes in a week, preview it. We've got what 15 problem 15 questions. This is like the bass forecast thing that I was saying you're going to be uploading there. So that one I have to grade, but everything else I think should be self-graded there. All right. So that being said, thanks for joining me. I'll stick around if you have any questions. If not, have a good night. Enjoy the warm weather, I suppose. Yeah. I guess those that are remote, thanks for joining me as well. Have a good night if you want to, or I'm here if you need any questions.
Again, I need to study to know what I need to ask, you know?
Yeah, that's all natural.
Yeah.
Yeah, it's at this point, is it normal to feel like absolutely confused?
Yes, that is part of the learning process. I
Okay.
mentioned that I gave a lecture / conversation about Claude Code, which is an LLM thing, this week to my peers at work, and I was in the same type of feel when they left. Is like, oh boy, that is powerful. I see what you're talking about, but I need time to digest what just happened. Yes.
Okay, good.
Luckily for you guys get YouTube videos. They do not.
Oh yeah, the YouTube videos help a lot.
Yes.
Yeah. The YouTube videos will still
Alrighty.
after the
Thanks,
class.
Brock. We'll see you next time.
Yep. Thanks, Fred. Have a good night.
Bye-bye,
Yeah.
you too.
The YouTube videos, I don't plan on taking that channel down in any way, time, or form. So
Oh yeah,
they'll be
the you know, put like unpublished
yeah.
videos.
As long as you keep the hold of the link, then
Okay.
they'll be there.